Now we're going to discuss planes in 3 dimensions. So just a reminder, a plane is determined by any 3 points that lie on it. In particular, they have to be non-collinear, so they can't lie on a straight line. That's just sort of the fine print details though. So we got 3 points. As long as they're not collinear, they determine a plane. You can think of this as if we've got a tabletop, we want to support it so it doesn't topple over or fall down. We want to make it stable. How many legs do we need to add to that tabletop to make it stable? We need at least 3 legs, and we need to add them in such a way that they don't lie in a straight line. So a plane is determined by 3 points that lie on it. How else can we determine a plane? Well, a plane can also be determined by a point on it. So a point on the plane. So just a single point now, not 3 points. And 2 vectors parallel to the plane. So if we have a point and we have 2 vectors that are parallel to the plane, we also say 2 vectors that lie in the plane, then that's enough to determine the plane as well. You can kind of think of this as if I have a point in space and I have 2 vectors that are coming out of that point in space, then that would determine a plane, because I can sort of rest stuff on it. So that's enough to determine a plane, a single point and 2 vectors. How else could we determine a plane? Well, we could use a point on the plane and 1 vector orthogonal or perpendicular or normal, these are all synonyms, orthogonal to the plane. So the idea is I have a point on the plane and I've got a vector that is perpendicular to the plane, and that's enough to determine the plane. So we will be interested in being able to go between these different descriptions. If we're given 3 points, we should be able to find a point and 2 vectors, or a point and a normal vector. If we're given a point and a normal vector, we should be able to find a point and 2 vectors, or 3 points on the plane. We should be able to go between all of these descriptors of a plane. And the reason being is because sometimes information will be given to us in one way, and we need to extract more information about that plane in order to write down an equation. So that leads us to finding the equation of a plane. Imagine we've got these 3 points. So we've got P1, P2, P3. Let's label them. They define a plane, and what we're interested in is coming up with an equation for that plane. What does it mean to come up with an equation for the plane? It means that I'd like to come up with an equation so that for any point Q in space, Q satisfies that equation precisely when it is a point on the plane. So I'd like to come up with an equation that Q has to satisfy to guarantee it's on the plane. How can we do that? Well, from these 3 points, we can construct 2 vectors. So we'll construct those 2 vectors. This one's the P1, P2 vector. This one's the P1, P3 vector. Once we've got 2 vectors parallel to the plane, we can take their cross product and get a vector that's perpendicular to the plane. Let's call that vector n. So we can construct this vector n, which is P1, P3 cross P1, P2. And this is a vector that is, so n is orthogonal to all vectors parallel to the plane. So that's its property. It's perpendicular to the plane. So any vector in the plane, it's perpendicular to it. Now I'd like to come up with a condition that Q has to satisfy to be in the plane. Well, what I can do is I can look at the vector that goes from P1 out to Q. Sort of missed that, so I'll make Q a bit bigger. There we go, now it points right to it. What does Q have to satisfy? Q is in the plane if and only if we have that this vector P1 to Q, so P1 to Q, is perpendicular to N. So if and only if it's perpendicular to this vector N. And an equivalent statement to that, and this is where we get an equation, is that they are perpendicular precisely when N dot P1Q is equal to 0. And so there is our equation of the plane. The equation of the plane is the set of all points Q such that N dot the vector from P1 to Q is equal to 0. Now we'll unpack this a little bit more. We'll start using coordinates and components for our vectors, but let's work our way up to that. Okay, so there's our equation of our plane. Let's go ahead and see how we can modify this equation to get some more equations for the plane. So the vector equation of the plane passing through the point, given by its position vector r0 and normal vector n, is this expression here, n dot r minus r0. Let's see where that comes from. It actually comes from our picture up above and our description up above, but here's the idea. We've got a point in the plane. Here, I'll draw the plane first. So there's our plane. We've got some coordinate system, some frame of reference here. And we've got our point on the plane, which is given by position vector r0. Then we've got this other point. This is the arbitrary point in the plane. We're trying to come up with an equation that it must satisfy to live in the plane. So I'll go ahead and I'll write down its position vector. That's what we're going to call r. So that's our arbitrary point Q. And now we've got the vector that goes from the point we know to the point we're trying to characterize as being in the plane. And that's given by r minus r0. If n is our normal vector to our plane, so there's our normal vector, then it has to be perpendicular to r minus r0. And so that's our equation, is that n has to be perpendicular to r minus r0 in order for r to be the position vector of a point in the plane. But this is true precisely when n dot r minus r0 is equal to 0. And so that is really just our equation we had up above, where instead of using points P1 and Q, we've used position vectors r0 and r. So let's unpack this a little bit more. So if we let r0 be the vector x0, y0, z0, in other words, x0, y0, z0 is the point on the plane, r be the vector x, y, z, so in other words, the point Q is given by coordinates x, y, z. That's our arbitrary point on our plane. Oh, and one more thing, we'll let n be given by a, b, and c. Then what does our equation become? Then this becomes a, b, c dot x minus x0, y minus y0, z minus z0 is equal to 0, or in other words, a times x minus x0 plus b times y minus y naught plus c times z minus z naught is equal to 0. And so there is the equation of a plane. A, B, C, they're given. They're the components of the normal vector of the plane. X naught, Y naught, Z naught, they're given. They're the known point on the plane, the known coordinates of the point on the plane. What we wanted to do is come up with a condition on a point, x, y, z, for it to be on the plane, and that's our condition. X, y, z have to satisfy this equation in order for it to be a point on the plane. And that's what we've got written down below. This is called the scalar equation of the plane, and we've written it again out here. And so you can see the parallels in 2 dimensions. Equations of lines are essentially things like y equals mx plus b, or in the most general form, an equation of a line would be essentially an equation like this, but there would be no z coordinate. There'd be no z component. So this would be the equation of a line in 2 dimensions. When we go up a dimension, a linear equation in x, y, and z determines a plane in 3 dimensions. If we expanded this out and moved all the constants to the right-hand side, then we get this standard form for the equation of a plane. And from this, we can read immediately what the normal vector to the plane is. It's given by ABC. What we can't see immediately is a given point on the plane, but we could find various points on the plane. I could set x equals 0, y equals 0, and then therefore z is equal to d over c. Gives me 1 point on the plane. I can find various other points on the plane. Whereas this previous one, I can read immediately 1 point off the plane, x naught, y naught, z naught. So there's some benefits to having the expression in one form over the other in terms of what information you want. All right, let's go ahead and do an example. We are going to write out the equation of the indicated plane. So it's a plane that passes through the point 5, 7, negative 6 and is parallel to the xz plane. So what we're going to do is we're going to think about those bits of information we need to determine a plane. 3 points, a point and 2 vectors in the plane, or a point and a normal vector to the plane. What kinds of information do I have here? Well, I need a point on the plane, and I have a point on the plane. 5, 7, negative 6 is given to me. I also need a normal vector to the plane. Do I have a normal vector? Well, I know my plane has to be parallel to the xz plane. So I do have a normal vector. The normal vector to the plane I'm trying to construct is precisely the normal vector to the plane that it's parallel to. And the xz plane has the normal vector of j hat, or 0, 1, 0. So the normal, n, is given by j hat, or 0, 1, 0. So I have a point, I have a normal, so therefore I can write down the equation of the plane. It is the x component of the normal times x minus the x coordinate of the point I know, plus the y component of the normal times y minus the y coordinate of the point I know, plus the z component of the normal times z minus the z coordinate of the point I know, and that's equal to 0. So these are both 0, and therefore we get the equation y minus 7 is equal to 0, or y is equal to 7. So there is the equation of the plane. Let's have a look at another example. We want to find the equation of the plane that passes through the point 5, 1, 4 and is parallel to this plane. So the plane I'm looking for has to be parallel to this one. So that means it will have a normal vector that is in the same direction as the normal vector to this plane. I can read off the normal vector from this plane right away. It's 2, 3, 4. So for the plane I'm looking for, do I have a point on it? Yep, 5, 1, 4. Do I have a normal vector to it? Yep, it's given by 2, 3, 4. So now I can find the equation of the plane. The equation of the plane is the normal vector, first component, times x minus 5 plus 3 times y minus 1 plus 4 times z minus 4 is equal to 0. So there's the equation of the plane. We can immediately see that this plane that I've just written down has normal vector 2, 3, 4 and passes through the point 5, 1, 4. That's just from the anatomy of how the equation is written. We can do a little bit of simplification if we want. 2x plus 3y plus 4z. So that's dealing with all the variables on one side, pushing everything else to the other side. What do we get? We get 2 times negative 5 is 10. So 10 comes over also with a 3 coming over and a 16 coming over. So I get a 10 plus a 3 plus a 16. So we get 2x plus 3y plus 4z is equal to 29. And so there is the equation of the plane. Let's look at the next example. We want to find the equation of the plane that passes through the point 2, 4, 6 and contains this line. So I'm just going to get a visual for this. It's going to have to contain this line, and we want the plane that contains that line. So that line would go on, forever, and so would the plane for that matter. But there's our line. And we also want it to pass through the point 2, 4, 6. So there's our point P given by 2, 4, 6. How do I know the point P is not on the line? I could do a quick check. If it's to be on the line, there'd have to be a single t value that when I plug t into the equation for the line, it gives me the value 2, 4, 6. But looking at the z component, for example, that tells me that t'd have to be a half. But if t was a half, then the y component would be 5, and it's not, because 3 plus 4 times a half would be 5, but the point P in question has a y value of 4. So just a quick inspection, P's not on the line. We also should realize that P is probably not on this line, because if it was, then there doesn't exist a unique plane that passes through this line. So because we're looking for a unique plane in this case, it stands to reason that this point is probably not on the line we're given. Alright, so what do we have then? Well, I can read off, thinking about the information I need 3 points to determine a plane, a point and 2 vectors, or a point and a normal vector. Right now I have a point and a line, but from the line I can read off a point on that line, 7, 3, 5. So I know there's a point 7, 3, 5 that's on the line and therefore in the plane. I also have a vector in the direction of the line, and that vector is negative 3, 4, 2. We'll call that vector v1, let's say. And with those bits of information, I can then find another vector in the plane. And this vector, let's call it v2. That vector would be tip minus tail, so it would be 2 minus 7, that's negative 5, 4 minus 3, that's 1, and 6 minus 5, that's 1. So now I have 2 vectors in the plane. That tells me then I can go ahead and construct a normal to the plane. That's really what I'm interested in, is getting a normal to the plane. So I'll do v2 cross v1 to get that normal. What is v2 cross v1? Well, it's v2 is negative 5, 1, 1 cross v1, negative 3, 4, 2. Go ahead and do the cross product. I'll just bring the number from the second vector down below so that I can go ahead and use our memory aid. So the first component, I cross out the first components of the 2 vectors, and I go 1 times 2 minus 1 times 4. So 2 minus 4, or negative 2. The next component, cancel out that one, be negative 5 times 2, that's negative 10. Negative 10 minus minus 3, so negative 10 plus 3 is negative 7. But then we take negative of that because we're in the middle component here, so that's a 7. And then the last one is Negative 5 times 4, that's negative 20, plus 3 is negative 17. So there's our normal vector, and so therefore our plane is going to be negative 2 times x minus the x-coordinate of the point we know. We can use any point we know. We'll use the 2, 4, 6, the one that's given. So it's x minus 2 plus 7 times y minus 4 plus negative 17 times z minus 6 is equal to 0. So there we go. If we want to clean it up a little bit, we can go negative 2x plus 7y minus 17z is equal to, so that'd be a minus 4 plus 28, and then a minus 6 times 17, so that's 60 plus 42 is 102. And so negative 2x plus 7y minus 17z is equal to negative 106 plus 28, so that is negative 78. And we could scale through this whole thing by negative 1 just to get 2x minus 7y plus 17z is equal to 78. And so there is the equation of our plane. Now we could do a quick double check. Right? Did we get this right? Did we make any mistakes? Let's go to math3d.org. We'll go ahead and get rid of the surface that's given to us. And what do we want? We want to find a plane that passes through a given point and containing a given line. So let's go ahead and plot that point and that line. So the point is 2, 4, 6. We'll get rid of these extra zeros. We also want a line, and the line is 7 minus 3t, 3 plus 4t, and 5 plus 2t. So there is our point and our line. We'll zoom out a little bit. And we wanted the plane that contained both of these. Well, let's see if our plane does the trick. So how are we going to plot our plane? We're going to use an explicit surface. Actually, we can use implicit as well, either one. We'll go implicit because that way we can just type in the full equation without having to write z is equal to something in terms of x and y. Instead, we'll just write it all in. 2 times x minus 7 times y plus 17 times z, and that's equal to 78. And it looks like, oh, does it actually pass through the point and the line? Well, we need to extend it a little bit more. So maybe we'll bump these up. I'll just make them really big. So x goes from negative 50 to 50. Everything goes from negative 50 to 50. And so, yes, it is a plane that contains the point and the line. I'll put a little bit of opacity in here. Make it so it's a little bit transparent. We'll make it 50%. And so now we can see that the point and the line lie on this plane. So there we go. Not only did we calculate the equation of the plane, we also plotted it to verify that our calculation was correct. Let's have a look at the next example. Find the angle between the following planes. Okay, so what is the angle between planes? Well, the idea is if we have a plane, and maybe I'll sketch another plane in here as well. So we've got another plane too. Then the angle between these planes might be kind of hard to get a feel for what it is. The idea is as follows. If I look at a side-on view, so if I look at it from the side, then what I will see is basically a line and another line. So that's our side view, and that's the angle we're interested in. We're interested in the acute angle between the planes. There'll be an acute angle, an angle that's less than 90 degrees or 90 degrees or less, and there'll be an obtuse angle, an angle that's between 90 and 180 degrees. We want the acute angle. And so how are we going to get that? Well, the idea is I know how to get the normal vector to each of these planes. So there's one normal vector, and here's another normal vector. Now, those normal vectors I can take to be in either direction. So what I'm going to do is I'm going to, instead of draw that normal vector to the green plane as going up in that direction, I'll draw it coming down. Okay, so there I've got our normal vector to the green plane. I've got our normal vector to the orange plane. And the angle between these two vectors is precisely the angle between the two planes. All that happened here was there was a rotation by 90 degrees. So if we rotated the two vectors counterclockwise by 90 degrees, we will land back on the line segments representing the two planes. So the idea is the angle that I'm interested in finding, I can find it by computing the angle between two vectors. So what we have is the angle between the two planes is the acute angle between the normals. And how do we compute the acute angle between the normals? Well, we know how to compute the angle between normal vectors, so let's just label these. This will be maybe the normal vector to the first one. This will be the normal vector to the second one. We can go ahead and find those normal vectors. So n1 is going to be 3, negative 2, 1. And the normal vector to the second plane is 2, 3, negative 2. And I want to find the acute angle between n1 and n2. Now I'm saying acute angle between them because I've got two vectors here. Who knows, the vectors may look like this. They may have an obtuse angle between them. But I'm just interested in the normals. So I would rather then pick the vector that goes in the opposite direction to get the acute angle between them. This is because normal vectors can point in either direction. I could take a normal vector and negate it, and I still have a normal vector. So I really don't care about the normal vectors up to sine. That's the bottom line here. I don't care about them up to sine. So if I want to find the angle between them, then I'm really interested in cosine of theta is equal to the dot product of the two of them over their lengths. This is the relationship between the angle between two vectors and the dot product. And if they just happen to point in opposite directions, then that means I would have the dot product that gives me a value which is negative. I'd instead rather take one of the vectors to point in the opposite direction by negating it. I can deal with all that fine detail stuff by just slapping absolute value signs around the whole thing, and that's sufficient. So then I go ahead and compute the dot product of these two. That would be 3 times 2, which is 6, minus 2 times 3, which is negative 6, and then minus 2 times 1, which is negative 2. All of that is over, so in the first case, the length is the square root of 9 plus 4 plus 1, or root 14, and in the second case, it's the square root of 4 plus 9 plus 4, or 17. And we see that the numerator really was negative. All that means is that these two vectors, they have an obtuse angle between them. So it's a good thing I slapped an absolute value sign on them because I'd really want to negate one of them. And so then I can, with the absolute value, I get the top is just 2, and the bottom is root 14 and root 17. So in other words, theta is equal to arc cosine of 2 over root 14 times root 17. And so there is the angle between those two planes. So the next question asks us to find parametric equations for the line of intersection. So we have these two planes, we want to find their line of intersection. So what I'd like to do is solve the equations for the planes. So those two equations, I'd like to solve them simultaneously. What are the x, y, z values that satisfy both of those equations? So this is a linear system. And I'm going to, rather than just start plugging away and using techniques from linear algebra to solve this system, I'm going to notice that there's a coefficient of 1 in front of z. So that means when I write down the linear system I'm interested in solving, I'm going to bring the z out to the front. So it will be z minus 2y plus 3x is equal to 5, and negative 2z plus 3y plus 2x is equal to 3. So now when I write down the matrix, the augmented matrix for the linear system, I have a 1 in that first row, first column. That's the reason I rearranged my variables. Having a 1 there, as you know from linear algebra, is really nice in doing row operations. So now we can go ahead and do our row operations. We're going to multiply the first row by 2 and add it to the second one. And so that gives me a 0, and negative 4 plus 3 is negative 1, and 6 plus 2 is 8, and 10 plus 3 is 13. And so now we will use this entry to go ahead and wipe out the negative 2 by taking negative 2 times the second row and adding it to the first row. So we've got our second row, which will remain unchanged. Negative 2 times 0 plus 1 is 1. Negative 2 times negative 1 is 2. Plus negative 2 is 0. That's the whole reason we're doing multiplying by negative 2 and adding it to the first row, was to make that term 0. Negative 2 times 8 is negative 16, plus 3 is negative 13, and negative 2 times 13 is negative 26, plus 5 is negative 21. And so now we see that there is a free variable. There's a free variable. This column represents our free variable column. There's a couple of pivot positions and then a free variable column. What does the column correspond to? Again, if we look back at our equations, remember we reversed the order to make our row operations simpler. So this tells me then that x is our free variable, so x is t. The last equation is negative y is equal to 13 minus 8x, or y is equal to negative 13 plus 8t. And the first line of that row-reduced augmented matrix is z is equal to negative 21 plus 13t. And so there are the parametric equations for the line of intersection of these two planes. You know, once we've computed this, we can read off something from it. So for example, this is a line. What's the direction vector? We've got a direction vector. The direction vector is 1, 8, 13. So what do we know about this direction vector? Well, it's got to be a vector that lives in both planes, because the line lives in both planes. So that vector has to live in both planes. What does that mean if that vector lives in both planes, where each plane we know the normal vector for already? That tells me that n1.v1 and n2.v2 have to both be 0. Well, this could detect some errors if we happen to make any. So we could do a quick check. You know, dotting n1 with v1, well, maybe I'll leave it to you. I'll just say check. check n1 dot v1 is equal to 0 and n2 dot v1 is equal to 0. All right, let's have a look at the last example. Okay, we want to find the distance from this point to the plane. So let's start with a picture. We've got our point P. It's not on the plane. You can check that just by plugging x, y, z, the values 1, 2, and 3, and for that into the equation of the plane, and you won't get the value of 5 coming out. So that's not a point on the plane. What we'd like to know is how far away this point is from the plane. That distance is going to be the length of this line segment, where we've got a line segment that goes from the plane, which is perpendicular to the plane, up through the point P. And we'd like to know how long is that. Let's call that length d. So that's the distance between our point and our plane. Now in order to figure that out, what we're going to do is we're going to take our equation of our plane and extract a few things from it. We're going to find a point on our plane. So a point on the plane. There are many. We really just need to find any x, y, z values that satisfy this equation. I'm going to look for the most straightforward one to find, and that is if x is 0 and y is 0, then z has to be 5 to satisfy that equation. So there's my point Q, 0, 0, 5. We also have a normal to the plane. You can read that off from the equation as well. I'm exaggerating this normal quite a bit, but there it is. It's 3, -2, and 1. Now, what is this distance d? Well, the idea is there's this vector we can construct from P out to Q. And if I construct that vector from P to Q, and I look at the component that it has in the n direction, so that's our projection of v onto n, then the length of that projection is precisely the distance between the point and the plane, because that is this vector here as well. Those vectors are equal. Oh, and I forgot to label v. V is this vector from P to Q. So v is our, from Q to P. So that's our vector. And we're looking for the projection of it onto n and its length. So that is d is going to be the length of the projection of v onto n. That is the length of v dot n divided by the length of n squared times n. That's our projection. We want the magnitude or the length of that, so that's the absolute value of v dot n over the length of n. What is v dot n? Well, v, let's go ahead and write it down in terms of its components. It's tip minus tail, so the point P minus the point Q, so it's 1, 2, -2. And so the dot product between v and n is going to be 1 times 3, which is 3, -4, -2. And all of that's over the length of n. And the length of n is the square root of 9 plus 4 plus 1. Or in other words, it's 3 over root 14. And so there is the distance from our point P to our plane. All right, that's it for this section. Thanks very much for watching, and we'll see you again next time.